And in this episode, we're going to look at classification problem as a part of supervised learning that is addressed by linear models we considered at the previous episode. So, what should be adjusted to the vanilla linear regression to be applicable to a variety of classification problems? So let's have a look at an example. So we have two-dimensional feature space x1 and x2, and a set of points colored in blue and orange. So we want to be able to separate those two sets with a linear regression model. One of the naive approach would be to learn an approximation in the form of theta transposed over x. So it would be like a two-dimensional plane in three-dimensional space. So and if you take a sign as a indicator of the class, like +1 for positive class for blue, and -1 as for the negative class, so this plane would could fit into the data in such a way that it can separate those classes in a reasonable way. So as we solve this linear regression problem with mean squared error laws and apply a sign as a solution to this problem. Let us have a look at the drawbacks or shortcomings this approach might have. It becomes obvious when you have more realistic data distributions, and in particular when your data is either unbalanced, or data have different spread. So because of the loss function, it introduces some correction, or it introduces an unnecessary shift towards the far away examples, or towards the class that has bigger population. So unbalanced is when you have blue much larger number than orange, and spread when it is wider than the other class in terms of Euclidean metric, or metric that is that your loss functions is sensitive to. So because of MSE takes into account those distant objects that tries to somehow take those into account, it doesn't plot an ideal separation curve. So instead of ideal decision boundary, which looked like this, we might get something not very applicable. So how can we adjust our loss function to address this problem? So as we mentioned previously, intuition about the data and problem at hand allows to play with the formulation of the loss functions, and we'll have a look at some different examples. So one example is called probability of an error. So we estimate the average over the sum of those components. So it is theta txi, so it is a predicted value multiplied by ground truth, and ground truth in this case either -1 or +1, and we want to check if this multiplication is below 0. So if it is negative, it means that we have an error of classification. So those signs of prediction and the ground truth do not match. So it is just another way to write down the error of our classifier. And we can plot the dependency of this loss function from the theta. And you can see an obvious problem which forbids optimization of this function using methods that we saw previously, because it is piecewise constant. So if you take a derivative in every point, it is either equal to 0 or it's like infinity in the corner place. Although methods that can help deal with such things exist, we try to find an approximation to this function. So we want to identify an upper bound that can be optimized instead. So here on this plot you have this function 0, 1 loss here using the blue color line, and several examples. So it could be maximum of 0 and the difference between 1 and m, or it could be just exponential of minus m, or you can think of many other examples. And the difference between those upper bounds and the original is that those upper bounds are differentiable. And this brings us to the idea of logistic regression. So in this formalism, we try to model the class probabilities by our function f hat, instead of trying to model the exact answers, exact classes. And for this, we can apply a technique that is called maximum log likelihood. So it is a little bit different from optimization technique that we looked previously, or approach that instead of minimizing error, it maximizes the likelihood of the probabilities being selected correctly. So likelihood is a multiplication of all probabilities in our dataset being selected correctly. So we can write it in the following way. Or if we want to maximize the likelihood, we just put this thing into the argmax term, into argmax function, and in this case, it can be expanded into sum of two components. The first component is when we have a positive label, and in that case we're interested in logarithm of the f theta hat of xi. Or if we have a negative labels, then we're interested in maximization of this term. And theta that corresponds to maximum of this function predicts the class with the highest probability. So how do we map the output of our model that predicts values from -1 to 1 to probability value in the range from 0 to 1? It's rather straightforward. So if we have an arbitrary function, output of the function x, or we can map into interval 0, 1 using this sigmoid function. And in that case, we can call the probability of the class 1 of the x to belong to class 1 to be the output of sigmoid function that takes as an argument output of our linear model. So, and such construction allow us to imply the meaning of this output of the regression, linear regression, as the log odds ratio between two classes. So if you compute this logarithm of the ratio of two classes, you will get exactly the output of the linear regression. So, and if we bring it all into the same optimization method, so we have loss function defined in the similar way as we saw before, but with negative sign in front of it. And minimizing this thing is equal to maximizing the likelihood function. And here we just introduce sigmoid function, just replacing this thing with this thing, and this thing with this thing. And then it becomes a very compact and concise expression that we can use as a function for gradient descent optimization. So let's have a look at an example. If we apply the approach that we mentioned before to the data set that is unbalanced with different spread, etc., the boundary is sitting at exactly right place. And you see that there are two corresponding lines, boundaries of blue class and orange class, that correspond to the probabilities of very high belonging to class +1 positive class and correspondingly to the negative class. So when classes are linearly separable for any correct decision boundary, we can see that any model of matrix theta can be changed to C theta for some C larger than 1, a real number. So it will still keep the boundary at the same place. And also it will improve the loss. And an ideal fit will happen when the sigmoid function turns into a step function with infinitely large theta matrix. And when your classes do overlap, the loss has some finite minimum, and prediction class probabilities change smoothly as you go from one boundary to another. And the values you see, as you see at the plot, are a little bit smoother. So from binary classification, you can intuitively get to multiple class classification problems. So it is called one versus the rest strategy. So for each class K, we train a binary model that separates the given class from all others. So it is not labels of this class, using the same approach. And the output of those function as class core for multiple class classification will be used for optimization problem. And very intuitive example, when we have 3 classes, we would separate looking by eye into something like this. But if we solve it using linear regression, logistic regression approach, for class 1 versus the rest, it would be boundary like this. For class 2 versus the rest, it would be this boundary, and this boundary for the third class. So if we combine those binary decision boundaries, we get something like this, and we can add decision boundary, like solving this argmax problem, which is quite natural for this scenario. And we get the final decision for this problem. Okay, and this was basically all I wanted to mention during this episode. So we considered a classification problem with linear regression and mean squared loss, and we saw how biased such solution could be, and examined the 1-0 loss function, which looks better, but it's hard to optimize directly. Instead, we introduced the upper differentiable bounds for the 0-1 loss that can be optimized instead. And logistic regression is a combination of those approaches, gradient descent of loss function of the upper bound optimization using linear model of the input feature. And a binary linear classifier can be adapted to a multi-class problem using 1 versus the rest strategy. This is pretty much understandable, I hope. And the quiz for you would be for the case of classifying d-dimensional data into k classes using logistic regression with a bias term. How many scalar parameters do we need to fit? And you have to choose something among those options.